resonance, and then we can just start with the hydrocarbon, right?
Okay, sir.
So resonance, you understood that resonance and hyperconjugation and inductive effect. Inductive effect is just actually the pushing of electrons, okay, of the sigma bond towards the more electronegative atom, or wherever the plus charge is. Got it?
Yes, sir.
Yeah. So carbocation, what is the stability? Just could you please recall and let me let recap whatever the stability of carbocation and how they were classified. Just little bit you can try. Because it is going to be very useful for us as soon as we are starting with the 12th class. Okay, we will have this topic, right? So you have these cations in front of you. Just you can try a little bit. No matter if it goes wrong, just let me know. Okay, I will explain it. So what do you understand by the stability of carbocation? How they are stable? How their stability changes with the increase in number of alkyl group, and what those alkyl groups are, how they're contributing towards the stability of the carbocation. Getting a point? So first of all, how many different types of carbocations? What does carbocation? So if you have a carbon positive charge, okay, that happens when the carbon has incomplete bonds. Clear?
Yes, sir.
So where it happens when you have incomplete bond on the carbon. You have a cation on the carbon, plus charge on the carbon. That is the carbocation, right?
Yes,
And the
sir.
carbocation can be methyl CH3 plus. Okay, this is the methyl cation. You have ethyl cation, right?
Yes, sir.
And this is also the primary cation. Primary means because where the cation is present, the plus charge is present, that carbon is connected to one carbon. Okay. Secondary, right?
Yes, sir.
Tertiary, right? Got it. Tertiary means
Yes.
a carbon carrying the positive charge. So how that stability is changing? Just you can try and I will help you out. No matter if it goes wrong. Okay, don't worry about making mistake. Okay, mistakes are good because we learn that we know that where we can go wrong. Right. It's important to do the mistakes. Okay, because they help us to for future be future ready. Right. So. You have methyl group CH3 groups, okay, CH3, 1 CH3, 2 CH3, 3 CH3, okay. And these are small, this whole group, ethyl group or isopropyl or tertiary butyl group, this one is tertiary butyl, can be considered as a small methyl groups attached to the carbocation, okay. And I have circled them. And these CH3 groups will exert what weight effect? They are going to exert the plus I effect, right?
Yes, sir.
Plus electron donating groups are there. These are the electron donating groups. Okay, they will exert the plus I effect, right? And so they are going to shift this electron slightly toward the positive charge, and the positive charge will become more stable. Clear or not?
Yes, sir.
So positive charge is going to become more stable. So the primary methyl cation, and then you have ethyl cation. Ethyl is more stable. Okay. Isopropyl is more stable, and tertiary butyl is further more stable. That's what we have discussed. It is because of the inductive effect and the hyperconjugation of the methyl groups. Got it?
Yes, sir.
Hyperconjugation, these are known as alpha hydrogen. They contribute towards the hyperconjugation. Clear?
Mm.
And more and more alkyl groups, and the alkyl groups bring in the hydrogens also along with them, right?
Mm.
So you have more hydrogens, you have more alpha hydrogens, right? More and more alpha hydrogens means more hyperconjugation. Each one of them can participate in hyperconjugation, so more stability. But these are the carbon ions. Clear?
Yes, sir.
So in carbon ion, minus charge is there. Minus charge is electron rich or electron deficient. What do you feel? Is it electron rich or deficient?
No. Sir.
Carbon ion are electron rich species, okay? Because they have more electrons on them.
Mm.
They carry negative charge, okay? They are electron rich. Clear? And
Yes, sir.
so because they are more electron rich, how their stability will get affected by the CH3 groups or present on them. You can try explain me a little bit. I will help you out.
Because they are rich, the other carbons will be moving away from it because there is enough.
Because more and more methyl groups, more and more plus sign.
Mm.
Getting a point, because these alkyl groups are actually electron donating groups. Okay, they will push the whatever the bond is there, they will push their electron to the other side away from them. Okay, so what
Mm.
is going to happen on these carbon atom? This was already minus, right?
Yes, sir.
And because it was already minus, because of these electron pushing tendencies, they became more minus. Okay, it became more minus. So it has moved away from neutral charge. It is becoming more and more negative. Means less and less stable. Is it clear?
Yes, sir.
So this I hope is clear. Okay,
Mm.
and primary, secondary, tertiary is least stable. Next is which carbocation is more stable, A or B? And what are the effects which are stabilizing it?
So A is more stable.
Yes. Why?
It is in tertiary.
It is.
The tertiary.
It is primary. Okay, because it is this carbocation is
Mm.
connected to only one carbon. This is also primary, but that is true that A is more stable. It has positive charge.
Tertiary.
Okay.
Mm.
So positive charge, how the positive charge is going to become more and more stable if it gets electron or if the electron are taken away from it.
Mm.
If it, because positive charge doesn't have any electron. Okay. So if
Yes.
the electrons are given to it, it will become more stable. Got it? If it
Yes.
gets more electron, it will become more stable. Getting my point or not?
Yes, sir.
But if the electrons are being taken away, because it doesn't have any electrons, so it need electron to get stabilized, because positive charge need to have more electron, because that it doesn't have any electron. Is it clear or not?
Yes, sir.
So how positive, where the positive charge is more stable, where it is getting the electrons, that we need to think. Getting my point?
Like where it's going to go?
It is going to be more stable in A. Okay. Why? This is a pi bond. Okay. Double bond. And this is having some loose electrons on it. Okay. So it can accept the electron. Right?
Yes.
Clear? So A is more stable. While how the B is stabilized? A and B. Yeah, Maha, good evening. Am I audible?
Good evening, sir. Yes.
Yeah, just we have started with the discussion of stability of carbocation, and I was discussing with Nabila about A and B about the stability. So you can also tell me how they are stabilized. Nabila is trying this problem, and you can also try. Which cation is more stable?
So what's happening in A?
A. A has some pi electrons, double bond. Getting about
Yeah.
these pi electrons, the sigma electron is like this. Okay, sigma bond is
Single bond.
a single bond. Yeah, it is formed by axial overlapping. These are the two atoms. The sigma electrons are between the atoms. The pi bond are formed by p orbitals, which are not all along the axis. They are actually above and perpendicular to the axis. So they have loose electron density. Okay, it can be given on the other side if there is some atom which is capable of accepting the electrons. Got it?
So like,
Is
is
it?
there a breakage of double bond over there, or like what? What does
Yeah,
the arrow signify?
breakage of double bond. The electrons will be shifted on this side. I will bring these two electrons this side. Okay. And what I am doing, what I am trying to do, I have shown it with the help of the arrow. Right, Nabila?
Yes.
So, Nabila, you had plus charge here. And Ma, you can see that the plus charge now it is going to come over here. Why?
Maybe because the cluster should be at the uh like the molecule where it has single bond.
Yeah, because that electrons are shifted on the left hand side and being taken away from the CH2. Okay, so now the CH2 will carry the plus charge. Got it? Clear or not?
But so there's not really much of a difference above the.
Yeah, yeah, not much of a difference. Okay, but which is the actual structure? Uh, Above one or the lower one? Both have same structure.
Isn't
Okay.
it the same thing?
Yeah, it is just the same thing, but actual structure. This phenomena is known as Nabila?
Yes.
Resonance. Is it clear? So resonance is actually delocalization of pi electrons. If the pi electrons can move here or there, right? Is it clear? Lone pairs, single electron, odd electrons. Those are known as odd electrons are known as free radicals. Okay. So actual structure is the weighted average of both the structures, right? So how you do the actual structure? In actual structure, the plus charge is neither this side nor that side. Okay. It is equally distributed. So this bond is double bond, this bond is single bond, and actual molecule it will be somewhere between double and single. This is single, that is double, so it will be between single and double, right? Is it clear?
Yes.
This is
Yes.
delta positive, partial positive charge. Okay, because what the charge on this carbon, it will be the average of 0 and 1, some half positive, right? E by 2. What is the charge on this carbon? That is E by 2. The plus charge actually distributes. So actually structure, the double bond is not on one side. It is equally distributed. And that is more stable. That causes more stability. Clear
Can
or
you
not? Now this is,
Yes.
it causes more stability because the positive charge is distributed and the pi electrons are also distributed on both the sides.
Okay.
Getting a point?
Yeah.
So this is the actual structure. What this actual structure is known as? And what are those
Resonance.
two structures? Yeah, resonance hybrid. And the above one is known as resonance structures. Okay, now please. This positive charge got the electron from the nearby double bond. And that led the, because of that, the positive charge was able to delocalize. Is it clear?
Yeah.
On two carbon atom. And that actually made it more stable. Is it clear or not?
Yes, sir.
And Nabila, what this second one is? What all stabilizations can be there on the second one?
We can make it CH2 and add a
What all
double bond.
effects this second carbocation can experience and how they are going to stabilize, help this positive charge to get lowered. Got it?
Mm. We can move from
Hmm.
left side one of the hydrogen.
Yeah. Is the positive charge, can it undergo resonance?
I don't think so.
Why?
Because there's only all single bonds.
And there are only single bonds. Exactly. Okay. So it cannot undergo resonance. Can it get electron in a way in which the left cation received from the pi bond? Can it receive the electron like this?
So I don't understand what you just said.
This cation was getting electrons from the pi bond. Nearby
Yeah.
pi bond was there. Okay, can it get electron like this from the pi electrons like this? Because it can't get, because there is no pi electron,
Yeah.
right? There are only sigma bonds. So no resonance. It is not resonance stabilized. So it is stabilized by what all factors?
Equal distribution of electrons.
Mhm. Which effect? Resonance, inductive, hyperconjugation.
Resonance.
This one. I'm talking about this. Can it undergo resonance?
No.
It cannot undergo. Why, Nabila, it cannot undergo resonance?
The hydrogens.
No pi electrons are there, no double bonds are there.
Mm.
Got it? So it cannot undergo resonance. Okay. So if it cannot be stabilized by resonance, it is stabilized by what other factors? That's what I'm trying to ask. I hope both of you understood my concern, my question. What are the factors which are stabilizing this cation? Is it stabilized by resonance? No.
Induction.
Yeah, something like that. Resonance? No, it cannot do resonance. Okay. It is stabilized by inductive effect. Navila, is it clear?
Yes.
So what about hyperconjugation?
Yes. And it is stabilized by hyperconjugation. Is this clear? How
Yeah.
resonance cannot happen. How
Mm.
hyperconjugation can happen and how inductive effect can happen. Can you explain it to me? Navila Ma, both of you, can you try to explain me how I should show the inductive effect and how should I show the resonance effect?
Like we,
Stabilize. In
for
this,
inductive acid basically
hmm,
means like shifting of electrons.
shifting of electrons, complete transfer of electron, like the one
Yeah, like
which we,
permanent transfer.
yeah, and of which type of electrons?
Mm.
Sigma bond.
Yes. So this is a methyl group. This will exert plus I effect. Got it? Is it
Yes.
clear?
Yeah.
Yes.
So this is one thing. This is plus I effect. I will show it on the sigma bond. And how will I show the hyperconjugation structures? How should I show the hyperconjugation?
By transferring electrons into empty spaces.
Transferring electron to the cation of the CH bond. Is it clear?
Yeah.
So I will shift these electrons of the CH bond. This is one of the hyperconjugation structures. This is the other hyperconjugation structure in which I have shifted the electrons from the other CH form. Okay.
Why do we write H plus alone?
Yeah,
Why do we write that H plus?
actually, why I'm writing, because if these electrons in hyperconjugation CH bond participate, they give their electron to the cation or the double bond, and then these electron get towards the cation. Okay, you have H plus left. Okay, or this H can also participate. So I will make this H as H plus, or this H can also participate. So turn by turn, all three can participate because all three are present on the carbon adjacent to the C plus. Got it. So this is the hyperconjugation effect. Is it clear or not? Maha
Yes.
and Nabila, how to write the hyperconjugation structures? Okay. And so we will do one question also that was from JE actually, but a good question can be discussed for school level also, but it was good. Okay, just I will let you know after this discussion. So which cation is more stable? Extent of stabilization is more by resonance. Then hyperconjugation, and then the stabilization happens due to inductive. Is it clear?
Yes, sir.
Okay, plus I plus H. Okay, so the first one is more stable cation. It is the resonance stabilized cation. Okay, more stable. Clear?
Okay. Yes, sir.
So this type of question appeared in JEE, okay, integer type problem on NEET or in boards also. Very easy question. So it is of all levels. Okay. So the question asks, how many hyperconjugation structures are possible in which you will see the participation of CH bonds in hyperconjugation? So first try to understand the question. Okay, this is a carbocation, just like this cation. Okay, and the adjacent CH bonds will participate in hyperconjugation. Okay, so that you can tell me. Getting my point?
So can I repeat?
Yeah. Question is clear. Just read it and let me know. Have you understood the question?
Yeah.
The problem is it clear?
Yeah.
So basically it is asking how many CH bonds are participating in the hyperconjugation. If I put it in a simple way, is it clear, Nabila?
Yes, sir.
So how many CH bonds are participating in the hyperconjugation in the above case, this one?
One.
Hmm? In this one, this molecule, how many CH bonds are participating? Total.
There will be only CC bonds.
Yeah, but this cation was stabilized by hyperconjugation. Okay, that you can see it happening in the lower structures I have shown. Is it clear? So I am asking how many CH bond participated in hyperconjugation in the above structure. This one, the previous problem. How many CH bonds you can see it participating with the cation?
36, 5.
This is one. Like there are 5 CH bonds you can see in the structure, but all of them are not
But
participating.
not all of them are not participating in.
The one who are adjacent neighbors. Nabila, can you see it? The neighboring carbon atoms, they can participate. They are known as alpha hydrogens, right?
Yes, sir.
So these are the 3 CH bonds, which actually one by one we have shown. Okay, that's why you can see H plus here, H plus on this, and H plus on the lower one, which I have not written. I can write it here. Okay, all the 3 participated because they were just adjacent to the C plus. Got it?
Yes,
So
sir.
they participated in the hyperconjugation. So just you can apply the same trick on this formula, this structure. This is from JEE, but it is can be asked in the school also because it is a very basic problem. It can be asked in NEET also because it is a very basic problem. So you need to count the CH bonds participating in hyperconjugation. Is it clear or not? The question is clear.
Yeah.
Yes, sir.
You should invest your time in understanding the question. Okay, that is very, very important. Okay, once you are
Maybe 3 over here.
hmm,
3.
how many? 3.
Yeah, I
I
think
will
so.
give you options also. Okay. 3. Option B 2. Option C 6. Option D 7. Is it clear or not? Question. So just
Yes,
you
sir.
need to, this is a bond line structure, you need to write or imagine. If you don't write, imagine it in this way. The bond structure. Yeah, Maha, Nabila, what are your answers? You can just share. First, you can. Cation is on where the cation is. Cation is on this carbon atom. Got it.
Is it 7?
Clear? Hmm? Yes. 7, 6, 5. What is the answer? 4, 3, 2, 1. Yeah, why 7 you are telling? You are very close to the actual answer. Ma, would you like to try?
6.
6. Why 6?
Because you said
Because I said
she
no.
was
I can
closer
say
to
that.
the
Yeah,
right
okay.
answer. So 6 was
Okay, I would have given 8 also, right? Then,
yeah, but you didn't, right? So maybe 6.
Is it
hmm,
not 5?
no, actually, look, if I try to draw it in the actual structure, this is CH3, right? This is what? CH2. Is it clear? And
Yeah.
this is what?
Yes.
CH.
Mm.
Okay. So, how many carbon atoms, adjacent carbon atom, and how many hydrogen do they carry? They carry 3 plus 2
10.
plus 1. Is it clear?
Yes.
I was correct, right? It was 6.
Yeah, yeah, yeah. So, but I wanted you to give the more actual answer. Okay. Right? So, very easy question. And is this cation undergoing resonance? Yes or no?
No.
No, because there are no double bonds, right?
Yeah.
Mm.
Compare the stabilities of these following cations. Following free radicals. What are free radicals?
There are some free atoms.
Yeah, they have free unpaired electrons, single electron. These are known as free
Lone
radicals.
pairs, right?
Lone pair is actually this one. If you have a lone pair, it will be minus. That is a carbon ion.
Okay.
Minus charge. Okay. If you do not have electron, that is a plus charge, carbocation. But if you have just electron, one electron, it is free radical. Got it?
Okay.
Yes.
So how many alpha hydrogens are there? And how they are stabilized? Have you understood what are free radicals?
You have the structures with the free electrons.
Yeah, free and single unpaired electron. They are neither positive nor negative. They carry unpaired electron. Single unpaired electron. These are intermediates. Okay, they are formed in the reaction. Okay, how free
Okay.
radical? What type of bond cleavage lead to the formation of free radicals? What type of bond cleavage lead to the formation of free radicals? How they are formed? First, tell me in a simple way how they are formed, how they are generated.
When
They are
there's a bond
generated
in
when the
between
bond
elements, there will be
break.
one electron that won't be in the bond.
Yeah, one electron on each bond. Got it? Each atom, separating atom. You cut the bond equally. That is homolytic bond cleavage. Got it? Nabila?
Mm.
Homolytic Maha means what? Homolysis means what? The bond is cut equally and
Like
the
the
two
bond breaking.
electrons hmm, and the electrons are one electron are given to each atom. Okay. So how free radicals are generated and what are free radicals? How they are generated? These are the species or the intermediate reaction intermediate which carry just one electron on the carbon, unpaired electron, one extra that unpaired
It is
electron on the
basically
carbon.
structures that just have single electrons known as radicals.
Yeah, unpaired electrons. Yes, single unpaired electron, they are called radicals. Got it? And how they are
Mm.
Yeah.
generated? In how they are formed in the reactions. We will see many reactions in which involve the formation of free radicals. In just next chapter, all hydrocarbon only we are going to see them. Clear?
Yes.
Yeah.
In hydrocarbon only we are going to see them, right? So are they resonance stabilized? Are they stabilized by
They won't
resonance?
have resonance, right?
Yeah, why they are not resonance stabilized?
Because only sigma bonds are present.
Only sigma bonds are there. Correct. There are no double bond adjacent to these, but they could have participated in the resonance if they are carrying the double bonds. Okay, on the adjoining carbon atom, then they could have participated. Got it? But here
Yes,
there
sir.
is no case of resonance. Okay. So how they are stabilized? Actually, what I have done is I am changing the number of methyl So you can see.
Maybe
Okay.
adding one more hydrogen.
Yeah, so more and more methyls are groups are being added in on every subsequent radical. This is methyl CH3 radical, that is ethyl radical, that is primary. This is secondary because the carbon atom carrying the radical is connected to two carbon atom, and this is tertiary. Clear?
Yeah.
Yes.
Got it?
Yes, sir.
So what will the presence of methyl groups is going to make them more stable or less stable? The presence of CH3. What CH3 groups will exert? What all effects CH3 groups can exert on this free radical?
Maybe the third degree one will be the most stable because
Yes,
more
the tertiary.
carbon atoms are present.
Yeah. So one is, this is, first of all, tell me whether it is electron rich or deficient. Does it have excess electron or less electron than the excess?
Which
Its
one?
electron, these radicals, what type of species are they? Electron rich or deficient? They
Electron
are electron.
rich.
No, actually they are electron deficient. Okay, why they are deficient? Because they are not having negative charge. They are having just some charges, not charges, just one electron. Not complete electrons are not there. So they are basically electron deficient species, but not as deficient as the cations. Cations are more deficient. Got it? Is it clear?
Yes, sir.
Yeah.
Yes, sir.
So these are the electron deficient species, and presence of methyl group, how it is going to cause more stabilization or less stabilization? What it is going to cause? More stabilization or less stabilization?
Mhm.
Yeah, because it is electron deficient, so it is going to cause more stabilization. Okay, you are going to have more stabilization with the presence of methyl groups. They are going to exert more plus I effect. Okay, this is one thing. The another thing is hyperconjugation. There is going to be more hyperconjugation with the increase in number of methyl, because these methyl groups are carrying.
Delocalize that
Pardon?
because hyperconjugate delocalize likes the free electrons, right?
Hmm. And there are you need the hydrogen on the adjacent carbon atoms. Is it clear?
Mm.
So you have the hydrogen on the adjacent carbon atoms, okay, and they are increasing. So how many alpha hydrogens are there? How many alpha hydrogens are there on each one of them? How many alpha hydrogens on methyl? Zero. Alpha hydrogens mean the hydrogen next to this carbon atom bearing the radical. Is it clear or not? There are three
Yes,
alpha
sir.
hydrogens. there are 6 alpha hydrogens and there are 9 alpha hydrogens. So, is it clear?
Yeah.
Yes, sir.
Got it. So more and more alpha hydrogens, more and more hyperconjugation can happen. Is it clear or not?
It's great.
And more stability. So I will just write the hyperconjugation for this ethyl radical. In order to draw the hyperconjugation, I am writing it in a more detail with all the bonds shown clearly, CH bonds. Got it?
Mm.
So you have just one electron, what will happen? This one electron and this will form a bond, and the H with the one electron will be shown like this. Clear or not? Not only this hydrogen, the next one. This hydrogen can also do it in the same way in which the above hydrogen did. And this hydrogen also. Clear?
Yeah.
So 3 hydrogens turn by turn, they can let their bonded electron participate in hyperconjugation with the C reactor. Got it?
Yes, sir.
Yeah.
So it involves the hyperconjugation structures involve how many CH bonds? 3. Is it clear? And in this isopropyl, the next one, which is the next one, okay, how many CH bonds are involved? How many CH bonds are involved in the next one?
In the second one, you're asking?
Yeah, in the secondary cation. Secondary radical, not cation. How many CH bond involvement is there in hyperconjugation?
Two.
There is, yeah, 2 carbon atoms are there, but how many hydrogen do they carry?
Four.
4 had.
No, not 4. There's CH3 and CH3. I'm talking about the 6. So 6 hyperconjugation structures are there. So this is going to be more stable than the previous one. Is it clear?
I thought you were asking about the below picture.
No, not this one. This I was asking for secondary. Okay, and similarly you can answer for tertiary also. How many hydrogen can participate in hyperconjugation?
9.
9.
Mm.
So it is going to become more and more stable with the involvement of hyperconjugation. But if there is an involvement of resonance also, then its stability is going to enhance further. Is it clear or not?
Yes, sir.
Yeah.
Got it?
Yes.
So this I hope is clear. Okay. Suppose if you have this radical, free radical, which is double next to double bond. This is resonance stabilized. Okay. Here, and this is more stable
Yes.
than the above one. Okay. Why it is more stable? Because what effect you are observing in? There is a pi bond, double bond.
Resonance.
Yeah, this is the resonance. Okay. And resonance actually the electron get transferred completely. Okay. The pi bonds get transferred completely. So resonance actually causes more stabilization. Is it clear or not?
Yes, sir.
Got it. Right?
Yeah.
Okay. These resonance structures we have seen. Now let's talk about the stability of resonance structures. Okay. So suppose if you have a cation, this is a cation. Cation is electron rich or deficient? What kind of intermediate is it?
Electron deficient.
Is it electron deficient or it, yeah, electron deficient? Why?
Because cations are generally electron deficient.
Yeah, because the cation, yeah, it is not having complete electron. That's why it is carrying less number of electron. That's why it is carrying the positive charge, right? It is electron deficient. Absolutely correct. Okay. And it is being adjacent to the oxygen. Okay. And because it is being adjacent to the oxygen, what all effects are exhibited by the oxygen on this cation?
Single bond.
There is a single bond to which this cation is connected to its neighboring oxygen atom. Got it?
Carrying.
Hmm?
Yes.
There is,
Providing electrons.
there are,
Providing electrons for CH.
there is actually oxygen is lone pair, so there is a resonance happening. This can pull the lone pair and let them get involved in the bond formation. Is it clear or not?
So there will be a pi
Mm.
formation, pi bond formation.
Yeah, there will be a double bond formation, pi bond formation, absolutely correct. But now the positive charge, because the carbon got its electron, so the positive charge will be
But then,
there.
sir,
Yeah,
there's like two lone. It has two lone pairs, right? So what about
but
the
now
other lone pair?
you're left with only one.
So we won't do anything about it.
No, but two loan pair because already that loan pair, the one of them at a time you can just involve one. Both of them can't go overlap. So you have a
It
double
can go
bond.
to the other bond, right? To the
Where?
CH3.
But it's why the CH3 is going to take. It's already having its complete bond. There is no shortage of electrons.
Oh, okay.
Got it? It's completely full. All bonds are sigma bonds. So I will not do it in this direction. Nabila, is this clear or not?
Yes, sir.
So, which is this phenomena which I have shown by writing these two structures of a cation?
Resonance structures, right?
This is
Hybrid.
resonance. Yeah, yeah, resonance. What is the actual structure? This is the hybrid. Got it?
Yeah.
Clear? So, which is more stable, A or B?
B,
Why?
because the carbon on the
Okay.
left side is becoming more stable by having four more.
Yeah, Nabila, would you like to add?
Yes, the double bond is also there.
Pardon?
The double bond.
Yeah, actually, this B is more stable because of complete octet of all atoms. Is it clear or not? Complete octet means 8 electrons. Got it? Clear?
Yes, sir.
So this is going to be more stable. Resonance stabilized, right?
Yeah.
Let's try some other resonance structures and let's compare their stability. This is which functional group?
These are esters, right?
Yeah, this is ester. Yeah, exactly. So C double bond O and OH was carboxylic acid. Okay, and C double bond, instead of OH you have O and carbon, that is ester, right?
Mm.
And this is methyl ethanoate. Got it? That's what the name is, methyl, and that whole portion of CO is the parent chain, alkanoate. Okay, there are two carbon on the parent chain. Okay, the one which is on the left hand side. So that is called ethanoate. O8 is the suffix for the esters. Is it clear
But like
or not?
only the first structure is a proper ester, right?
Yeah, first structure is the proper ester, exactly. Actually, the other structures are not the proper. I mean, they are the resonance structure because what I am doing is I'm just shuffling the pi electrons lone pair among them. Is it clear?
Yeah.
Yes.
But does those structure even exist?
Does those structure even exist? Yes, good question. Actually, the actual structure is the hybrid of all these structures. Got it? That's what resonance is. Okay, agreed or not? So these are the resonance structure, but some are highly unstable and some are very stable. So we
Okay,
need
so the
to
first structure is basically the hybrid of all these structures.
no, first structure is the normal, actually. No, not the first structure. The hybrid will be the mixed form of all these structures. Okay, but there are some structures
Yeah.
which will not exist. Some structures are written in an absolutely incorrect way. So you will not consider them
Like
in
the third
resonance.
structure. So is the fourth one.
Fourth one, yeah, we need to discuss that, right? So accordingly, and by looking at the charges and by looking at the octet of the each individual atoms, we need to compare the stability of the following resonance structures of the given resonance structures. Got it?
Yeah.
Yes.
Here, PQRS. So which one do you consider to be more stable? Which one do you consider to be less stable? Okay.
The first one to be the most stable.
The first one to be the most stable. Yes. That's there is no problem, no issues with it. Okay. That's normal weight is written, right? That is the most stable, no charge. Okay. Neutral canonical structure is more stable than the charged one, right? So this is
Yeah.
neutral, this is more stable. Okay. P is more stable. Got it?
Mm. Yes, sir.
Nabila, is it clear? Because there is others are having either incomplete bond or they carry charges. Okay, so all those factors are going to make them unstable, right? P, Q. So P is the actual ester in which we write, but this is the most stable resonance. And which is the least stable?
S.
S is least stable. Why do you think so?
Because the double bond is wrong, right?
Double bond is wrong, but you have that appropriate charges also being put on the atom. So the first one is more stable, that is clear to both of you,
Yeah.
right? But Then look for the octet, which is the most important factor. So where the atoms have incomplete octet, 8 electrons. Suppose if the
Q
bonds
on
have
R.
been, yes. So where the octet is missing, in Q or in R?
At the C point over there.
In both, it is missing for an individual atom. Okay, it is missing for C plus. It is missing for O plus. Okay, but as though it has inappropriate bonds. Okay, bonds put in inappropriate manner, but they have all the atoms are still having complete set of 8 electrons. Nabila, is this clear or not?
Yes, sir.
So suppose if we consider this oxygen, how many electrons are there on a total? 8 electrons. Got it? 3 lone pairs are there and 1 bond is there, which carries 2 electrons. 8. Right?
Yeah.
What about this one? The lower oxygen, is it having 8 electrons, complete octet?
Yeah, it is.
Yeah, 3 bonds and 1 lone pair. Got it? So complete octet is there. Okay.
Yes.
Where the octet is incomplete. Where it is not complete. On the carbon, in the R, in the Q, it is incomplete on, it is not complete on the oxygen. Got it? Is it clear? So which is most unstable? Now you need to look for the charger. Both
We
have
have
positive
Q,
and negative charges. Hmm?
Q.
Yeah, so P and then S both have complete octet, okay, and these are unstable, okay. Q is more stable or less stable? Least or most?
Less.
Why less?
Because in R, like more bonds are there, right? Like the lone pairs and everything. Electrons are more over there
The
in R.
bonds are same. Total bonds are same in both. In R as well as in Q. You can count them. Total bonds are same. The octet is incomplete for carbon and there it is incomplete for oxygen. You need to look for the charge
Okay,
where
so
the
R is the least, right? Because more the lone pairs, less the stability.
But lone pairs are coming on electronegative atom. Negative charge is coming on electronegative atom. Is it clear? But that is not the case in first in Q. Positive charge on oxygen with incomplete octet. Are you getting my point?
Yeah.
Nabila, are you getting? Maha, are you getting? How many electrons are there on this oxygen? 6. And oxygen is what type of atom? Electronegative or
Electronegative,
electropositive?
negative.
Electronegative. So it, yeah, will it be happy with the positive charge? No. Electronegative atom will be stable if it carries negative charge. So here it is negative and here
Okay.
it is positive. Got it? Carbon is more electronegative or less electronegative as compared to oxygen now. Carbon, more or
Less
less?
electronegative.
Yeah, less electronegative. So less electronegative will like to have negative or positive charge on itself. Less electronegative.
Negative.
Will it like to have negative or positive? When it will be more stable? It is less electronegative. Less electronegative, understood? It's not more, it's less electric. So it will not be stabilized by negative charge, it will be stabilized by positive charge. The more electronegative will need to have negative charge on more electronegative atom and positive charge on less electronegative atom for stability. Is it clear?
Yes.
Got it?
Yeah.
Is it clear, Nabila?
Yes, sir.
So this is the stability. Here you have complete octet for both of them. One is neutral and another is charged with complete octet. Okay, this is incomplete octet, and then you need to look at the charges where the charges are coming. Positive charge is coming on electronegative atom or an electropositive atom. Is it clear or not? Got it? So this is a very famous molecule and used for household cleaning purpose. Which molecule is it?
Naphthalene.
No.
Naphthalene has two benzene rings.
Phenol.
Yeah, phenol. Okay. So phenol is having the lone pairs on oxygen. Okay. And the lone pairs are in conjugation with the double bond. There are three double bonds. Is it clear?
Yeah.
And there is a lone pair. This is on O. Lone pair is given to double bond. It is pushed towards lone pair can take the electrons or give the electrons. How should I write it? Is it the right way? Or should I write it in this way?
Yeah, the first.
The first white arrow is the right representation of the yellow one.
White one.
The white one. Because the lone pair are just sitting ideally, they can be shared with the double bond, right? Clear?
Yes, sir.
Yes.
And if the lone pairs are shared, they will form a bond. And these bond need to be shifted aside. Okay. So you will have a negative charge. Okay, there you have a positive charge. Okay. Then this lone pair can move, could push the pi bond. Okay. The negative charge will push the double bond ahead of it to the next atom. These are the resonance structures of the phenol. What this OH is exerting, what effect this OH group is exerting on the benzene?
Positive charge.
No, it's giving or taking electron, and by what means? Through inductive effect, resonance effect, hyperconjugation.
Resonance.
Yeah, this is the resonance. So this is the group which will exert plus R or mesomeric effect, plus M effect, one and the same. It's giving its electron through resonance to the pi bond because it carries lone pair, which can be shared with the pi bonds. Okay. Nabila, is this clear or not?
Yes, sir.
So you are having this benzene. And what's the, is there any inductive effect between the OH and the benzene?
Yes,
Yeah. And what effect, inductive effect this OH group is exerting?
it's permanently taking a bond.
It's permanently,
Taking a bond.
yeah, it is pulling the bonded electron towards itself, trying to pull this bonded electron towards itself. Bonded electrons towards itself, but this is minus I effect, okay? This one of the OH group. So this is more prominent or the plus R is more prominent? Whose effect is one, in a one way it is trying to pull the electrons.
Resonance more prominent over here.
Yeah, resonance is because there the electrons are getting transferred completely. Nabila, is this clear or not?
Yes, sir.
So resonance effect is it's giving electron to resonance, okay. And if we try to look at the hybrid, it is going to be like this. Delta plus, because if you type the average of all the structures, there will be some resonance structure have positive charge, some do not have positive charge. It will average will be some partial positive. This will be negative, this will be negative, this will be negative. Okay, these positions, these are known as the side positions of the benzene ring are known as ortho positions. Got it? Is it clear?
Yeah.
And
Yes.
the opposite one is known as the one which is directly opposite to a group, that is known as para. This is meta. This is para. This is meta. This is ortho. Is it clear?
Yes.
Yeah.
Ortho, meta, para. Okay.
So how do you name such stuff?
No, this is the common name. Otherwise, IUPAC name are very standard. You need to put the number on the OH and 3-methyl phenol or 2-methyl phenol. Okay. These are the common names. Got it?
Okay.
IUPAC names are systematic. They use that locants 1, 2, 3. Okay. But these common names are very common. You need to remember them. And very frequently they are being used. More frequently than the IUPAC names. So this is the resonance structure of the phenol. Okay. And this is how it gives the electron. And the resonance effect, if you see, it's not uh, transferring exactly to all the positions of the phenol. The ortho positions and the para positions, you can write this. Ortho and para are affected by resonance in benzene. In benzene, not in everywhere, okay? Not in all the rings. All the rings are not benzene. So ortho and para positions are affected by the resonance. Okay, if there is a plus R or plus M exerting group, that is going to bring in the negative charge on the ortho and para positions. And if there are electron withdrawing groups like minus R, NO2 is there, that is going to pull the pi electrons up. Okay, that is going to bring in the positive charge on the ortho and para positions. Is this clear or not?
Yeah.
Yes, sir.
So P, Q, R, S, and T. If I try to compare the stability, P and T are more stable because they are completely neutral and there is no issue with them. All the atoms are neutral, they have complete octet. The problem is with Q, R, and S. Okay, so Q and R are of equal stability because they are identical in terms of the distance between plus and minus, and then T. No, not Q. Q and S are identical, and then you have this not T, this is R. Then you have R because the positive and negative charges have moved away. So these are the stability of order of the resonance structures of the knot. And but actual structure is which one? Is it P, Q, R, or S, or T? Which one is the actual structure? What will you say?
The first one is the actual structure.
No, the actual structure will be the hybrid of all these structures. But
Okay.
because it is the resonance happening, right? And here the delocalization is happening between the lone pair and the pi electrons. And this is the hybrid. This is the actual structure which exists. Got it?
Yes, sir.
Okay, so let's cover the hydrocarbon. Let's start the hydrocarbon in the next class. And this thing is the preparation of hydrocarbon only. Okay, today whatever we discussed is going to be used in the reactions of hydrocarbon. So unofficially we have already started hydrocarbon, and next class we will going to start it completely. Okay, but all these applications of GOC are going to be used not only in hydrocarbon, in all their organic chemistry. So just go through your NCRT, and if there are any doubts of this chapter, let me know. So
Okay.
let me end the class. Okay. All right. Good night. Take care.
Thank you, sir. Bye. Take care.
Okay, bye.